Hi everybody, back to our YouTube Cook RT again. Today I'm going to talk about our Einstein relativity, which is part of the fundamental physics, and to make you more understand about what's going on in this theory. As there, you know that this is very famous, um, that we are talking about, for everyday life, and but somehow is people just know that when you're talking about relativity or something that you are associate with time and length, and that's also related to some physical factors, just like momentum, frequency, and velocity. So many things, and people understand about relativity is just like when you take the ship, go to our universe with the speed of light, and then you come back. It seems to be you get be younger than somebody is, stay on the earth. So let's go to see how these things work. Well, for special theory of relativity, Einstein proposed two postulates. The first one, here stated that the laws of physics are the same in every inertial frame of reference. So that means you can apply laws of physics that you have, even Newtonian mechanics that already exist, and that's be able to explain, about their situation that's happen around us, and also you'll be able to apply their Einstein postulate 1. And the second postulate, Einstein stated that the speed of light in a vacuum is the same in all inertial frames of reference and is dependent of the motion of the source. What does this mean is that if you have more than one reference inertial frames, the speed of light is going to be the same, and even the other frame is moving with velocity u. The light velocity is not going to change according to velocity u. Okay, this is Einstein's second postulate. Now let's see the more explanation of the first postulate. If you have if you are on a train moving with velocity v, and you look at people out of the train, and then you can tell how fast these people out of the train is moving, but you cannot tell how fast the train is moving because you are simply sitting on the train, and you cannot tell from your own reference velocity. You cannot tell, so you don't know what is your v. And for electromagnetic, for example, electromagnetic force, that electromagnetic force is going to be the change of your magnetic flux with respect to time. And if you look at two different ways, you have a permanent magnet, and you have this is coil, and if you move your permanent magnet into the coil, you can have electromagnetic force, or is going to induce the voltage. And if you look the other way, just make your permanent magnet at rest, and you move your coil into the permanent magnet. It also induces electromagnetic force, and two electromagnetic force from two situation here uh, is the same. So it's not different. It doesn't matter how you look at what frame of reference has to work out to be the same. Now for the second postulate. In case you have a spacecraft moving with velocity 100,000 meter per second respect to the Earth, and you're sitting on the Earth here, and I have our E as the Earth, and S prime is represent that the aircraft is actually in the S prime frame or S prime reference frame. And you're sitting on the Earth, look at the spacecraft, you're on the S frame or S reference frame. And if the spacecraft launch a missile, and if the velocity of the missile is 2000 meter per second respect to the S prime reference frame, that's why I have subscript here. M is represent missile, S prime is represent S prime frame. So when you look at the missile here, the velocity of the missile with respect to the Earth simply is going to be 2000 meter per second plus 1000 meter per second, and end up with 3000 meter per second. Now look at the other situation when you have something moving with velocity of light. In this case is the spacecraft just shine the light of the spacecraft. You know exactly that the velocity of the light with respect to the S prime reference frame is going to be the speed of light, and the velocity of the spacecraft with respect to S prime reference frame and respect to the Earth, if it's become 2000 meter per second, you probably compare to the problem here, and if you want to find the velocity of the light with respect to the Earth, you probably say that it's going to be equal to c plus the speed of the spacecraft. Sorry, this is supposed to be 1000, but actually you have the velocity of the light is become c, and this one c plus 1000 is going to be more than c, which is impossible, and we not allow that to happen. Okay, and we will discuss in more details later on, because that the maximum velocity of any kind of that exists in the world, in universe, is c, or is about 3.010 to the 8 meter per second. You cannot have velocity greater than that number, or greater than velocity of the light. Okay, so our reference frame, you're going to have a velocity of the light to be the same, or c. Okay, let's move to page number 2. Now, since we're talking about reference frames, let's take a look at the defining inertial frames of reference. If I have a particle P, and we will deal with two reference frames. One is S, the other one is S prime. And let's make the S prime reference frame moving from the left to the right with velocity v or u. So at the start, or at t equal to 0, two frames are at the same position, or it's overlap. And if I define the S frame with the red line and the S prime frame has the blue line, I define coordinate of the system on the S plane to be x, y, z. But since we are dealing with the reference frame moving from the left to the right, so the only x prime is changed, not y and z. So y and y prime, z and z prime still be the same, correct? And if you write out the relation between x and x prime when the time passed by t, you know that your x is going to be your x prime, right? Because we get it start right here. This is x prime plus ut. So that's, you get a coordinate x and y still equal to y prime and z still equal to z prime. So you end up with x equal to x prime plus ut when you were the velocity of the S prime frame moving from the left to the right. And this is we call Galilean or coordinate transformation. So when we're talking about x, y, z, we're talking about coordinate. Now you take a look at the velocity. The velocity of the S frame, you can write down as dx by dt, right? And Vs prime, you're probably thinking should be dx prime by dt, but somebody already know that, hey, this is not supposed to be t, it's supposed to be t prime. Okay, let's take a look at what happened if this one is become just t. And you know exactly that it's going to be t prime, right? So you take a look at this equation, you differentiate with respect to the time. You have dx by dt equal to d of x prime plus ut with respect to t. And then you have dx prime by dt plus differentiate of ut with respect to t. You end up with u. And you have finally you have vs equal to vs prime plus u, and this become Galilean velocity transformation, as I mentioned earlier here. This one is Galilean or coordinate transformation. So what happened if the S prime moving from the left to the right with velocity c, and that's mean that this is becomes c, and this one also becomes c prime plus u, which is impossible, right? Because Einstein's second postulate states that the light velocity in any reference frame has to be the same or become c. You cannot have the light velocity is greater than c. So in conclusion, you know that for this term you cannot write vs prime equal to the x prime by dt, but has to be your dt prime. Okay. Now take a look at some example to get better pictures. I'm talking about relativity of time intervals. Let's start with our S frame here. S prime frame. and on the right is the S frame. I have the light source and I have a mirror with a separation D, and the S prime is moving with the velocity u from the left to the right, and then the light is transmitted to the mirror and reflected back to the light source. So in this case, you define delta t0 is the time is take from the light, start from the light source, go to the mirror and back to the light source again. You can find delta t0 become the round trip, right, of the light source, the light throughout. So it simply become the distance divided by velocity, and the distance in this case it become 2d, and velocity of the light is c. So delta t0 equal to d over c. Now take a look at the S reference frame, which is at the actually this one is moving and this is stationary. What I mean is stationary is mean don't get confused. Stationary is mean just like if for in this case, if this one is on the train, right, the S frame is just like you are sitting and look at the train, you will see the light path look like this one here. Okay, don't get confused. Just look at the train here. So what the picture you see is going to be like this one here. So when the time pass by delta t with respect to your reference frame, which is S, so you have like t here, and the time of S prime is become t prime. When you look at the light path, it's going to be like this one here, and when the time pass by delta t, this distance is going to be u multiplied by delta t, because the train is moving with velocity u, right? Now look at this one. You still have the light source and the mirror here with the separation is d. So to find delta t, you have to find the length of the light, throughout. So it starts from the light source, let's go to the mirror and back to the light source again, and that's equal to 2L over the speed of light, which is c. Now you have to work out for L. Look at the picture, this is 90 degree, and half of this one is become u delta t over 2, so that's why I have here u delta t over 2, and then this one is the separation of the mirror and the light source is d. So ul equal to square root of d square plus u delta t over square, and the whole thing is square, and then you just plug in L here, and then you can find delta t. You rearrange the term, or from equation 1 and equation 2. I'll let you work this out by yourself. It's just simple math. You're going to end up with delta t, which is the equal to delta t0 divided by square root of 1 minus u square over c square. I have this one's wrong. Delta t is supposed to be in S frame, right? And this has to be your S prime frame. Delta t0 as shown in the picture. So this one also we call time dilation, or the Galilean time transformation. Let's just take a look at this example. If you have if this one, it doesn't move at all, so u is becomes 0. And definitely what you see when you're sitting outside here in the S frame, you're going to see the light path, just look like in the S prime frame. So of course your delta t is going to be equal to or delta t 0. And what happened if the S prime frame moving with velocity of c? You become c, and this end up to be 1, and 1 minus 1 becomes 0. You're going to have delta t very, very long. Okay, so your delta t is going to be your infinity. And that exactly, that's people talk about, when you are on a spacecraft or on something that moving with velocity c or the speed of light, your delta t, this mean people who sitting on the earth, right? Because t is the time on the S frame. It's going to be really, very long when the time on the S prime frame or the moving frame is there become much smaller than delta t. So that's why when people are talking, this is about the earth, and you just come back to the earth after you travel with the velocity of the speed of light. People here on the earth become an old man, right? And you're still young. Okay, so that's how you get the equation of the time dilation of the Galilean time transformation. Oops, I think I'm missing page number 3. And the time is going to get involved with the frequency as well. So that's why it affects so many physical parameters. Now let's get into more, let's take a look at more examples here. If you have a clock, like tick tock here, and one tick is take to be your delta t 0, and this is in the time in the S prime reference frame, and for example this one in the spacecraft, and the spacecraft will move with the velocity u, and you're sitting on the earth on the S reference frame. The time dilation are delta t equal to delta t 0 divided by square root 1 minus u square over c square. And you take a look at this one here. When you have a certain number of the time, this one going to be longer than this one. Okay, when you look at that one, the same as I explained earlier. Let's take a look at this one again here. If the S prime frame move with the velocity 0.99 c on the spacecraft here, you release okay, let's look back and to see, as I mentioned, this is going to be the clock will run for this problem. Delta t 0 is going to be less than delta t when you are sitting on the earth. Okay, and now look at the time dilation for the S prime frame move with velocity 0.990 c, and you take a look at the time dilation delta t equal to delta t 0 over 1 over 1 minus u square over c square. And you have to judge which one is going to be the proper time that you going to use, this one as the proper time. This can be either delta t or delta t0. Since when you on the spacecraft, it looks like this one, it doesn't move, but when you are on the S frame, you see the spacecraft moving. So this one is going to be at rest, okay, because you measure is on the spacecraft, and this one become the proper time. So or delta t0 is on S prime frame. It's become the proper time, and then you can calculate delta t to be this is, I did something wrong here, so actually let's ignore this one. It's become 15.6 10 to negative 6, and you compare to 2.2 10 to negative 6, and you know that this one is become a bigger number. So this one, I did something wrong here. You see that the time frame, or the time on the S frame, is going to be is greater than the time on the S prime frame, correct? This means the time here is shorter than the time that you see the light pulse last. So it lasts longer on the Earth when you are compared to the light pulse will last shorter, on the spacecraft. Another one is talking about muons, or unstable subatomic particles. You can see in cosmic ray in universe. You can see the light, is coming out in the sky. And we're talking about the decay time. It's take 2.2 10 to the negative 6 seconds for them to decay. But when the cosmic ray is moving with the speed of 0.990, and that's very close to the speed of light, when you look at the Earth, or you look at the cosmic ray in the sky, this is on your S frame. So to muon that you can see is become this one I did wrong too. It's supposed to be 15.6 10 to negative 6, which is longer than the time in the S prime frame. Actually, it take the time to decay to be 2.2 10 to the negative 6, but when you observe the cosmic ray in the sky, you will see that it lasts only 15.6. It's lasts longer. That's why you sometimes this one is already disappear, but you still be able to see what happened in the sky. So it's just like you look at something in the past, something that happened already. And this one also, you take a plane from San Francisco to New York, and distance is about 4.8 10 to the 6 meter, and the plane is moving with the velocity 300 meter per second. And now you have to make your judgment. You already have relation between of the time in the S frame and the time in the S prime frame, or time dilation. What do you need to judge? You need to judge which one is going to be the proper time. Okay, so you can plug in that number. So let's take a look at the plane moving with velocity 300 meter per second, and the distance from San Francisco to New York is 4.8, so you can find your time. The problem, the time here is going to be the time of which one. Of course, you're sitting and you see the plane flying, right? So it's become the time of the S frame, just like you're sitting, on the ground and look at the plane. Now you look at the airplane frame. You want to see, how they feel when you're sitting on the plane. How long the time is going to take. Instead of 1.6, 10 to the 4, 10 to the 4th second. Well, from the time dilation, you just plug in delta ts become this, our number here. So delta t0 s prime simply become delta ts multiplied by this term. So that's why I have, the number right out here. Okay. And just to remind you, sometimes you want to find the square root of 1 minus something. Look at this one. Just like Taylor series. When you want to expand this one, 1 minus a, when a is very small compared to 1 to the power of whatever, you're going to end up with 1 minus, the power multiplied by a to the power of 1, and then plus 1 over 2 square, and then multiplied by a square, and so on. And for a much less than 1, so the square term drop, so you have leftover term here is become 1 minus 1 over 2 a, right? So this is the time dilation. So you look at this one here, the time, when you compare the time here on the S frame, reference frame, or on the ground, on the earth, and this is the time, on the plane. Do you know that the time on the plane is shorter than the time, on the S frame? Okay. And I also have this part to make it simple. It's nothing much, because we already have for the time dilation, you have term 1 over square root 1 minus u square over c square. And I'm going to define this term as gamma, just to be make it more simple to write down. And u over c has become beta. So gamma equal to 1 over square root 1 minus beta square. You take a look at this one, the plot between gamma and your u. Okay, you can see this term gamma equal to 1 over square root 1 minus beta square. For u equal to 0, you have beta to be 0, so you end up gamma equal to 1, correct? So this one, the speed u is become 0. You start from here. And what happens when you have like increasing speed, or u increasing? The ratio here, when you have this one increasing, beta also increasing too. So 1 divided by smaller number, your gamma is getting bigger. And when beta equal to, when u equal to c, beta equal to 1. So you have 1 divided by 1 minus 1, or 1 divided by 0. You get gamma to be infinity. Okay, next, talking about we already mentioned about relativity of time, or the time frame. Now we're going to talk about relativity of length. Okay, this is going to get involved with so many physical parameters. Whatever that's in the unit of meter, that's always going to affect, by the relativity of length. First we will consider the length parallel to the relative motion. This means that if the reference frame moving from the left to the right with the velocity u, and the length that in the direction of x is going to change, but not y, but not z. Right? This is the meaning of whatever I wrote down here. So you take a look at S prime frame, same, and S frame. In the S prime frame, you have the length L0, and this is the light source, this is the mirror, and the S prime frame moving with the velocity from the left to the right with the speed of u. And then when the time delta t1 pass by, the mirror is going to move, is going to be at this point, and you have to measure from the start here to the time delta t1 pass by. You're going to have a new length to be d. This is what you're going to observe. So let's take a look at what can happen and how to derive the Galilean length transformation. Okay, let's take a look at from picture. You see that d is simply equal to L plus u delta t1, right? And also d equal to c delta t1. Why? Because you're talking about the light source here. The light travel for the time delta t1 is will travel for the distance of c delta t1, because you start shining light, from at the starting point here. When the time delta t1 pass by, the light gonna hit. It's going to be at this point. So simply you multiply c by delta t1, and of course your d they all have to be equal. So you make a c delta t1 has to be equal to this term, L plus u delta t1. You rearrange the term. You have delta t1 equal to L over c minus u. And of course this one we're talking about in our S frame, right? Now let's take a look at the return trip from the mirror to the source. This means you start shining the light, and the light hit the mirror and back to the light source again. Let's make it take another to delta t2. So delta t2 equal to what? Well, you can use this equation, okay, except because they have the same distance, right? For the light source to the mirror is never changed. But what happens when it's returned? Your u is going to be opposite sign. So you end up with delta t2 equal to L over c plus u. Or you can derive the same thing. So no problem if you want to derive. Because your light source going to move down here, right? When the time delta t2 pass by. So you can find the distance that you have to calculate. So this term simply become L minus u delta t1. Okay, but just for simplicity, let's take a look at this one. Just change the sign of u to be a positive u, because it's opposite direction of u. The first one, the light moving from the left to the right, and for the return, the light moving from the right to the left. So your u is become the opposite. And for round trip, delta t is equal to delta t1 plus d2. And then your substitute, or this is your delta t1, and this is your delta t2. You rearrange the term, because now you're interested in the length. You don't want the time. But you also are, you have delta t here, and you also are, okay, you have this equation equal to delta t, and you also have equation time dilation delta t0 equal to delta t multiplied by 1 minus u square over c square, and that's equal to L0 over c, as we did before. So you take this one delta t into the equation here, right? And this term still be the same. You rearrange the term because now you have a L0 and then L. That's what you're looking for the length transformation, Galilean or length transformation. So you have end up with L equal to L0 multiplied by 1 minus u square over c square, or that's we call length contraction, because when you start with the length L0 and this term become less than 1, you end up with L to be less than L0. We call length contraction. So the length in L measuring is reference frame in which the ruler is moving is shorter than the length L0 measured in S prime or referenced frame, or the S prime we consider is at rest. Just keep in mind that this is your S prime is moving, but for example you are on Earth, this is your S. You look at the length in S prime, which is the L0, and you look at the length that you are observed on the Earth on the S, and the length here is L. So don't confuse that why S prime is at rest, because L0 you are sitting on the spacecraft or on the frame that moving. You don't feel like how fast it's moving. So this one become like you are at rest. But when you observe, from S frame, you see the S prime frame moving with the velocity u. Okay, don't get confused about it. So that's I define this is very important, because when you want to relate, L and L0, you need to know which one is the proper length, or the number that given. Let's say that from problems to plug it in, because if you plug it in to be the wrong number, you get the wrong answer. So the proper length is the length measured in the frame in which the body is at rest. So in this case here, even has S prime frame moving with velocity u, and you are sitting on the Earth, and you observe the length in the S prime frame. This one is considered at rest, L0 and S prime. Even it's moving, but since L0, when you're sitting in S prime, you never know how fast the S prime frame is moving. So we consider that is at rest. Okay. Okay, just take a look at example to be better understand. I have a spacecraft moving with velocity 0.990 c, and I have L0 to be 400 meter. So this one we consider in its prime frame, right? And this measure to be a proper length because we consider this one is at rest. And if you're sitting on the earth, you look at the plane. What is the length in the plane you're going to see? Well, you need to use the Galilean length transformation. So you have duration L either S frame or earth equal to L0 multiplied by 1 minus beta square. So I plug it in L0 to be 400 meters. As you're moving with the speed of light 0.990 divided by c, so it end up to be this term square, and then you have the length to be 56.4 meter. Okay, so you can see that one shorter length, but the proper length is longer than the length in the S frame, which is opposite the time, right? For the time, the proper time on the spacecraft is going to be shorter than the time that you notice from the S frame when you are sitting on the earth and observe the time on the plane. So this is what I mentioned here. When you're sitting on the S frame, you're going to see the length in the plane to be 56.4 meter. So actually this one I do something opposite. If I have the frame, the length on the earth on the S frame to be 56.4 meter, and if you are sitting on the spacecraft here moving with velocity 0.990 c, what is the length you're going to see when you are from the spacecraft? Well, just to make you understand which one is going to be your proper length, it has to be this one, right? Why? Because it's at rest. Its measure is at rest, and when you on the spacecraft, you don't see the spacecraft moving, but you see the Earth moving, right? You don't feel like how fast the aircraft moving. So this has become the proper length. So this is very important. That's why I told you which one you need to find out, which one is the proper length. And you can find the relation here, L equal to L0 square root 1 minus beta square. And the proper length is become 56.4. Then you multiply by 1 the square root 1 minus beta square. So you end up with 5.96 meter. So this is what you're going to see when you sitting on the spacecraft and you look at the length on the earth, which is actually is the 56.4 meter, but you will see the length is 7.96 meter. So you can work out on the both ways or opposite way. Now our moving muons. We have the proper light time to be 2.2 10 to the 6. So for 1 second, if the cosmic ray is moving for 2.2 or 10 to negative 6, that means it will travel with the distance 653 meter. And if it have dilated lifetime, right? Time dilated, because they're just like we are talking about the time frame last time. You're going to have when you're sitting on the earth, actually when in the cosmic ray itself, it's already gone, but or it take about 2.2 10 to the negative 6 second, to decay. But for you to observe, the muons, you see that it takes longer than that 15 by 6, 10 negative 6. That's why you still see your, the muons in the sky, but actually it disappear already. Just like somebody say that maybe you look at the sun is still shining every day, but maybe the sun is already gone. Who knows, right? So it's the same case. Now you want to dealing with their length. Okay, this one is 12 with their D1 to be 656 meter. And for the later time, then there, that the cosmic ray travel with the velocity is 0.990 c. So you multiply with the time, it actually travel with their 4630 meter. And if you take a look at this one, you plug it in here to be your 4630 meter. Okay, this has become a proper time, right? Because you are here, and then you can calculate the length of the muon throughout in the sky here to be 653 meter. Okay, let's try to make yourself understand about what I'm trying to present here. What I want to point out at this point is that you look at this one here. When you have used the Galilean time transformation, you can find time in the S prime frame and S frame, and you can calculate the distance is travel, directly from S equal to V multiplied by T. And in this case is your time is 2 by 2 10 to negative 6, and the velocity is the 0.990 c. You end up d1 equal to 653 meter, and you do the same thing here. You have end up with the distance to be 4,630 meters. Or you can use the Galilean length transformation directly to find your new length. So it's out to be exactly the same thing. It doesn't matter you use the this equation or the Galilean length transformation. Okay. Okay, let's move to Lorentz transformations, which is consistent with the principle of relativity. You're probably wondering, when already earlier I've talked about S frame and S prime frame with coordinate on the S frame to be x, y, z, and also t, and S prime frame with the coordinate x prime, y prime, z prime, and t prime. So how they are related to each other. This is what we're going to do, and that's what we call Lorentz transformations. And it's very useful when you want to analyze, problem related to relativity. Let's take a look at this one here. This is the x or S frame, and the upper one is the S prime frame. Since we move along our x-axis, so y prime, y, and z doesn't change. So you're going to have y equal to y prime, z equal to z prime. But of course you know that x not equal to x prime and t not equal to t prime. And then you take a look at S prime frame moving with velocity u from the left to the right. And then you can see here, when you compare the coordinate x and x prime on the different reference frames, you can see obviously that your x equal to, or start from 0 here, become ut plus x prime, right, on the S frame itself. So this one become x. The same thing as for t equal to 0, you see that x equal to x prime is start from 0. And then your x prime, you use the you modify, because since x prime is moving, the S prime frame moving with velocity u, so you need to add or modify by square root 1 minus beta square. This is one is contracted term. Or you rearrange the term, you can find your x prime become x minus ut divided by square root of 1 minus beta square. So this has become Lorentz coordinate transformation. In this case, only x change. Also, you can do the same thing. You take a look at this one here. You look at this x prime or the S prime frame at rest, and x just moved to the left with velocity u. So you can write the same thing as the just change x to be x prime, and u, since it's moved on the opposite direction, you change the sign u to be negative sign here, and t has to be t prime because in there is prime reference frame, and x prime simply become x, and then you modify by the term square root 1 minus beta square. So if you compare two equations, then you have x prime here, simply and you derive x prime from this equation. You just put here and make it equal to this term, and you can rearrange the term later on. So I work out this for you, and then you already have x minus ut over square root 1 minus beta square equal to negative ut prime plus x square root 1 minus beta square. You rearrange the term because you want to find the relation between t prime, t, and x. And this has become a Lorentz time transformation. Okay. You can do this by yourself. Okay, let's make a move. So from x prime equal to x minus ut divided by square root 1 minus beta square, or you put 1 over square root 1 minus beta square become grammar phi dx is going to be your gamma is a constant, and then dx right here, and then u is constant, and then dt. So you end up with this equation. And what about t prime? T prime is do the same thing, right? You pick up this term right here, but in the form of grammar. dt prime equal to gamma, and then become dt, and u and c square is constant, and then x become dx. You want to find the velocity or Lorentz velocity transformation. What you can do is just simply divide dx prime by dt prime. Right? You pick up these two equations here. You get v prime. So our gamma cancel out, and then you have dx minus ut divided by your dt minus u dx over c squared. And then you divide both numerator and denominator by dt. So you have this one here, dx by dt become v, dt by dt become 1, dt by dt become 1, dx by dt is become v. And you can find the relation between v prime, or the velocity in s prime frame, and then the velocity in the s frame. And that's what we call Lorentz velocity transformation. And you can analyze this one. If, for example, is u becomes 0, so you have this one 0, this one 0, so v prime equal to v. It's not a big surprise, right? And what about if u become c? You can work this out by yourself again. Alright, so what happened? Okay, let's work together. U becomes c, and you have 1 over c here, so you multiply c, so this one drop to be become c. And then you have this term left only v, right? And so this one become what? This one becomes c, and u becomes c, and you have sorry, you have v over c left, and this becomes c, and this becomes c. So you have what? C, right? V prime becomes c. And now our same, or if you want to work around, and you want to look at this one as v in s frame, so you simply change v prime to be v and v to be v prime. You have to put the opposite sign from negative to be positive, and this one from 1, and this also change the sign to be positive. You end up with v equal to this one. This is also our Lorentz velocity transformation, and this is I showed you before, right? For this one is less than c, you simply v prime is approximately to be v, and if v equal to c, u equal to c, you end up with v prime equal to c. So as the second postulate of Einstein, that states that v equal to c for s and s prime frame, or in all reference frame. So you already know how to work out the Lorentz coordinate transformation, Lorentz time transformation, and also Lorentz velocity transformation. I just want to add it up this one for you here. What do we call, we call space-time diagrams. Okay, if you plot between our ct and x in the s frame, what happens if you want to put s prime frame, also on this ct and x plot? This one is made to make simpler, because this x is have the unit of meter, and ct also has the unit of meter, right? Because the unit is meter per second, and the t is the unit of second. So meter per second multiplied by time, which is second, so you end up with the same unit fx, which is meter. And this is what we call line, which is tell you the path of a particle from a line. Let's take a look at the slope of the line here. It's simply you differentiate this one with respect to x, right? Or the slope of the line is delta ct over delta x, or which is equal to tan theta. You know about that already, right? This is delta cx, and this is delta x, and the ratio of delta cx over delta x give you tan theta, and will give you the angle of the line. So when you differentiate this one, you have like c dt by the x, and the x by dt simply is v. So the slope of the lines give you c over v. This becomes the ratio of the light velocity over any velocity. For example, if you have v equal to c, your slope simply become what? 1, right? c over c is 1. So slope is equal to 1. The slope equal to tan theta. Tan theta equal to 1. Theta become 45 degree. So that's why you have this plot. And the other side, when you have v equal to negative c, you have the slope become negative 1, and you have tan of look like this one. The slope become negative here. And also, if v become 0, what happened? You get the slope to be infinity, right? Because c divided by 0 give you infinity, and tan 90 degrees give you infinity, so it's become a straight line here. Now, if you want to plot our S prime reference frame on the CT and X diagram, how can you do that? Let's start with on the CT prime axis, X prime equal to 0 all along, right? This means that if you take a look only at this axis, it's the same thing as you have CT and X. You want to plot along this line here. What is your x? Your x is 0, right? So that's why I wrote down here on CT prime axis, x prime equal to 0 all along. And then find the relation between CT prime and x, because you want to use the plot of the CT and x, but you want to plot our CT prime. So from the Lorentz coordinate transformation, you pick up this equation and you take a look at this one. When x prime equal to 0, this means along the CT axis, right? That's I explained already. When this one becomes 0, you have ut prime equal to x square root 1 minus u square over c square, and you find delta t prime over delta x. You move u to the right, you have 1 over u and square root 1 minus u square over c square. And if u over c is much less than 1, and even you have square term here, even drop very fast. So you don't have this term here. Become delta t prime over delta x prime equal to 1 over u. And what is this one here? It just look like you have ct prime equal to c over u multiplied by x. Okay, let's take a look at this one here. Why you have this term? Because from this equation here, you move delta x to the right, so it's become simply x, right? This has become t prime, and you multiply both by c, because you want to plot ct prime. So your ct prime simply become a c over u and then multiply by x. That's why I have the equation right here. So when you have like this is your x and this is your ct prime, you can find the angle of ct prime with respect to x axis. For example, if you have u equal to 0.6 c, the slope of the plot is become c over u, right? So c over 0.6 c, and you have your this is equal to tan theta. So your tan theta equal to 1 over 0.6, and then your theta is arctan of 1 over 0.60, so it's give you a 59.0 degree. So it's just give you the idea. This one become our 59.0 degree. Okay, so if you were trying to explain more in the next YouTube or about what's going on here, and let's take this one on x-axis ct prime equal to 0 or t prime equal to 0. From t prime equal to, this is the Lorentz time transformation, and you have a slope here u over c, and I just figure out and become theta equal to 31.0. So it's not so difficult for you to understand here. So in conclusion, you already know you define the time transformation, length transformation, coordinate transformation, and you know that when you have two different frame s and s prime, when one frame is moving with velocity, you know that how t here is going to be different than our t prime or t here, and also L, this has become L prime, right? And even x, and this is x prime, which is you have already have relations represented by many equations that I explained in this YouTube. And this one is going to affect our momentum and frequency and whatever so many physical parameters that you will see later on. Okay, so I'll see you in next YouTube.